In our video notes for Standard 16, we learned about both the law of sines and the law of cosines. So we're going to explore a little bit more one of the particular cases that we talked about at the end of those video notes, and that is when we know an angle and then two sides, okay? But those two sides don't both surround the angle. They're not both adjacent to the angle. So that's that angle side situation that we talked about. So here's one that we're going to look at. We're going to find all triangles that could have the following measurements. Alpha is 27 degrees, C is 75, and A is 40. And remember, our convention is that whenever we're working with these, alpha goes with A, beta goes with B, and gamma goes with C, because these are kind of the A, B, and C of the Greek alphabet. So what I'm going to do here is I'm going to try to sketch the best I can what I think this triangle may look like. So I'll try to make a 27-degree angle here, best I can. Okay, so we know that this is 27 degrees, and then this is supposed to be 75. And so then this one, the one opposite of alpha is 40, so it can't be too, we definitely want it to be shorter than that 75 there, so maybe do that with it. All right, so there's kind of the triangle that I'm thinking that I have. So one thing we know is that the law of sines is helpful here. So if let's mark down these things we're searching for. So if this is C right here, then this is gamma, and then that would mean this is B and this is beta. And so if we can find B, beta, and gamma, then we've solved this triangle. Oops. There we go. All right, so since I know this angle and its opposite side, I'm thinking that the law of sines is going to be helpful here. So I'm going to have 27, sine of 27 degrees over 40 is equal to the sine of this unknown angle, gamma, over 75. All right, and we can solve pretty easily for gamma. So we have the sine of gamma is equal to this, and I'm not going to be in a hurry to pick up my calculator because I don't want to do rounding on top of rounding within my problem. And so I get to this stage here where I'm ready to take the inverse sine on both sides. So we say the inverse sine of everything on the left should give me gamma. Okay, and if I plug this in my calculator, I get 58.3 degrees is approximately my gamma. So I can go up here and say that that's 58.3 degrees. And let's just kind of look at our picture. My picture is actually pretty good. That looks like it's an angle, a little less than 60 degrees. So I'm pretty happy with that. And then from there, I know that I can find my other angle, because all the angles of a triangle always have to add up to 180 degrees. So it's pretty easy to find beta by just saying we're going to take 180 degrees minus the 27 degrees minus the 58.3 degrees. And that, of course, gives me 94.7 degrees. All right, so I can put that up here as well, 94.7 degrees. And then finally for B, just to switch things up here, I could use the law of sines again, but I can definitely also use the law of cosines. So I can say B is equal to the square root. All right, and remember what we're going to do is we're going to look at 75 squared plus 40 squared minus 2 times 75 times 40. times that angle that's between them. And so that's going to be the cosine of 94.7 degrees. And so we get that B is approximately 87.8. And so that completes the problem, right? Actually, no. So at this point, what I've done is I have completed half of the problem, essentially. Okay, and what I mean by that is at this stage right here, when we said gamma is equal to 58.3 degrees, let's picture that on just the xy plane. So 58.3 degrees, maybe even let's talk about a unit circle. So 58.3 degrees, is right about there. So remember what got us 58.3 degrees was the idea that we were saying the sine of gamma has to equal this number. And so the answer to that question was the sine of gamma equals this number when you're at 58.3 degrees. But we know that on the unit circle, there's two places where you will have the same sine value. The other one is over here, right? And we learned from our work in earlier standards that you can always find this one by taking 180 minus the first. So this is 180 degrees minus 58.3 degrees. And that gives me 121.7 degrees. So at this stage, what we should have done is we should have said, okay, that's great that gamma is 58.3 degrees, but there's also an alternative. And that alternative is to say that my gamma could also have been 180 degrees minus the inverse sine. And of course, just as a reminder here, we're in degree mode, and you'll be in degree mode anytime you're working with these problems where you're solving triangles. Okay, and so that's going to give me my 121.7 degrees. Okay, so what does this mean? Well, what it means is there's actually a completely different triangle that's also a solution besides the one that I started to draw over here. Okay, so what does this one look like? We still have the 27 degrees, right? So we still have that. That hasn't changed. We still have 75, and then this other one still has to be 40. Okay, but here's what it looks like, because what are we saying? We're saying that our gamma, right? We're saying that that gamma is actually 121.7 degrees. And so that means that's got to be greater than 90 degrees, right? So we have an obtuse angle there. Okay, and then we still need to find B, and we still need to find beta. All right, so then from there, we go ahead and just do the same thing we did down here, right? So beta is going to be 180 degrees minus 27 degrees minus 121.7 degrees, which gives me 31.3 degrees. All right, so there's that beta that we're talking about. And then again, we could use the law of sines or the law of cosines, it doesn't really matter. But then B is going to be, if I use the law of cosines, the square root of still 75 squared plus 40 squared minus 2 times 75 times 40, but now it's the cosine of 31.3 degrees. So my B is approximately 45.8. So you have these two completely different triangles that are being produced here, that both follow this criteria that alpha is 27 degrees, C is 75, and A is 40. All right, so let's talk a little bit about what's causing these two solutions to occur. So when you have angle side side, so you know this angle, you know the side, this side adjacent to it, the angle, but then you also know the side opposite of that angle. There's a number of things that can happen. One thing that could happen is that this A here over on this side fails to be at least as long as the height of the triangle. And in such a case, basically, it just can't reach down to the bottom where it needs to go. And if that happens, then there's going to be no solution to your triangle. It could happen that A is exactly equal to the height of the triangle, and in that case, you're just going to get one solution. Another case is down here where this third one is what we just saw, where there's kind of two ways that it could have turned out. A could have been on, right here, but you also could have essentially swung it in like a door to be here and still preserve the same length, still preserve this angle and this side. But there's basically two ways you could orient that third side. And that's when you have two solutions like in our last example. And then finally, this one here, this is one where you just give one solution. And you can see what happens in these situations is that the opposite side of your angle is just way too long. And so there's no way to swing it through like we could in this one. And so you can definitely still just have one solution when it's impossible to swing it through. So we're going to look at a couple more examples that'll kind of show you how to recognize when you're in these situations in terms of the algebra. So let's look at example 2 together. All right, so solve the triangle where alpha equals 28 degrees, C equals 75, and A equals 34. So, we're going to try to sketch 28 degrees best we can. We'll call that 28 degrees. And we're saying that C, so this side, is supposed to be 75. And then we're supposed to have 34. So, you don't have to worry about being really accurate necessarily when you're first starting this. You're just trying to, get in the ballpark so that you can visualize in your mind what's happening. All right, so we know that just like in our example number 1, we would start this by saying the sine, and of course this is gamma here, right? The sine of gamma over 75 equals the sine of 28 over 34. And we can solve for gamma. So this will be the sine of gamma is equal to the sine of 28 degrees over 34 times 75. And then, just like we did in the last one, we take the sine inverse to find our gamma. Now, when you do this, what's going to happen is you're going to try to do your approximation, and then what's going to happen is in your calculator, it's not going to spit anything out. So in your calculator, it'll say error or something like that lets you know that something's wrong. Okay? And so if the calculator is saying error, that means that there is no solution. Now, why is it saying that there's an error? The reason it's saying that is because the thing you're trying to take the sine inverse of, actually let me just make a note of it right here. This thing right here, if you calculate that, that is 1.04. And remember that the sine is never more than 1, right? Sine oscillates between -1 and 1. So if you're trying to say the sine of gamma equals something bigger than 1, then you're in an impossible situation, and so you get no solution here. And like I said, your calculator will just basically tell you that you've got yourself an error. And more specifically, I can say what does mine say to me? It says error domain is what mine says. Okay, but that's the reason that it's occurring. So what does this mean? Well, this means that this graph that I made, or sorry, this picture I made wasn't really accurate. It's not true that this actually can make it all the way down. So what we're in is we're in the situation where 34 is not a long enough side to be able to reach all the way down to the base of this triangle. Okay, so to go back to that previous page, this no solution situation is the first one that was being described here. All right, so that's one thing that you might see. Let's look at example number 3. So it wants us to solve this triangle. So alpha is equal to 45 degrees. So I'll try my best to represent that. So 45, and I can do a little bit better than that, I think. So we'll say 45 degrees there. And then we've got, so alpha equals 45 degrees. Now let's see, we got to be a little bit careful here. A is supposed to be opposite, right? 7 roots of 2 is bigger than 7, for sure. So let's call this one 7. And then this one will be 7 roots of 2. It's got to be longer than that first one, right? 7 roots of 2 has got to be longer than 7. So I'll make it something like that. So 7 square roots of 2. All right, so here's kind of the triangle that we're talking about. All right, so we have the sine of 45 degrees over 7 roots of 2 is equal to, we'll call this beta. And by the way, in my first 2 examples, beta was the top angle. There's nothing special about that. It doesn't really matter. All that you need to get right is to make sure that when you have alpha and A, or beta and B, or gamma and C, that they're opposite of each other. Other than that, don't sweat, where the angles go in your picture. So we'll say the sine of beta divided by 7. All right, we can multiply by 7 on both sides. You get a little cancellation there, right? So this will be the sine of 45 degrees divided by the square root of 2 is equal to the sine of beta. And when you take the inverse sine of that, we honestly don't even need to take the inverse sine, since sine of 45 is a special value. And when you divide by root 2, you're going to get a nice value. But it's also okay just to do that. And what you're going to get is that beta is 30 degrees. Okay, and that kind of seems reasonable that we get 30 degrees there for that angle. Okay, now for a moment here, we got an angle, we got an answer, unlike the last example. So let's go back to example number 1. In example number 1, remember when we got this first angle, we realized, oh, you know what? We should have also come up with a second angle. We should have come up with 180 degrees minus our first angle. So, okay, maybe we should do that here. So let's, maybe do a different color just to understand we're talking about a different triangle. So here what I might do is say, okay, beta also could have been 180 degrees minus 30 degrees, which would be 150 degrees. Okay. But we need to be careful here. So what do we already know? We also know that we have 45 degrees. So what we can say is that 150 degrees is too big to be a solution. And the reason it's too big to be a solution is because 150 degrees plus 45 degrees is 195 degrees, right? And we know that it can't be larger than 180 degrees. So what we're finding here is that this thing, this idea of taking 180 minus the original, actually does not lead to a second solution. So that's okay though. All that means, going again back to our previous pictures, it means that we're in this last scenario where A is just too big compared to C in order to be able to swing it through and find a second triangle. So at this point we just say, okay, we're happy with this as a solution. So 30 degrees is my beta. My gamma then would be 180 degrees minus 45 degrees minus 30 degrees, which would be 105 degrees. All right, so that's this one here, gamma, 105 degrees. And then how about my C? Well, my C, if I use the law of cosines, will be the square root of 7 squared plus 7 roots of 2 squared minus 2 times 7 roots of 2 times the cosine of 105 degrees. And that gets me about 13.52. So 13.52. So that is our one and only triangle that solves these parameters here. All right, so I've given you a number of different scenarios that can occur. So this one here, I want you to give a shot to yourself. Hit pause on the video and try it out. You've seen a situation where there's two solutions. You've seen a situation where there's no solution. You've seen where there's one. So see if you can figure out what's happening on this one. So take a moment to do that, and then you can unpause once you've think you got it figured out, and you can see my solution. All right, so here I'm going to do my best to sketch a 47.74 degree angle. Gamma is opposite of this side, right? So the one that's touching the angle should be longer than the one opposite. So I'm going to do something like that. 47.74 degrees. And it's definitely an angle side-side situation, right? So, oops, almost put the wrong label on that. So that should be my 131.08. Okay, so with the idea that there's an angle side-side situation, I should already be thinking that two triangles is a possibility. So as I set up this first, so I'll call that alpha, beta, and B. As I set up my equation to find alpha, I'm thinking ahead that it's possible that I'll end up with two different triangles, so not just the one that I've sort of sketched out here right off the bat. All right, so I can multiply both sides by 131.08, so the sine of alpha is the sine of 47.74 degrees times 131.08, all divided by 97.84. So then alpha is going to be the sine inverse of all this. So 131.08 times the sine of 47.74 degrees, all over 97.84. And when I put that in the calculator, it gives me an approximation of 82.54 degrees. Okay, and this looks just shallow of 90 degrees, and so that's a good sign, right? That my picture, agrees reasonably well with the answer that it just came out. All right. Now, here is the spot, right? I want us to get in the habit. Here is the spot where we've got to check. So I know that I'm not finished with this yet, but I'm going to go ahead and say, well, it's possible. It is definitely possible that alpha could have been something else. Okay, so let's see. Alpha could have been perhaps 180 minus the sine inverse of all that stuff. And when I crank that out, I get alpha is approximately, what do I get? 97.46. Okay. All right, so what would that look like? Well, what that would look like is, I sketched this triangle up here. So I still got my 47.74 degree angle, right? This is still larger, 131.08. But then if this angle, if this alpha here is bigger than 90 degrees, then that means it's something like this. So here's what I've got. So we've got a picture like this one. So there's alpha, there's beta, and there's B. So alpha, 97.46. That seems reasonable, right? That we could be getting a triangle that's shaped more like that. So if so now I've got my two scenarios here. Let's see if they both in fact work out. So let's finish up the blue one first. So the blue one says, right, if that's my alpha, then my beta is 180 degrees minus 47.74 degrees minus the 82.54 degrees that we got for alpha, which gives me 49.72 degrees. And if I go back up to my picture, okay, do I believe that my beta is in fact 49.72 degrees? Well, honestly, it doesn't look very much like it. Okay, but let's really think about this for a second. This is a good lesson in, do I trust my picture or do I trust my algebra? In this case, as I take a second look at my picture, I think I'm going to trust my algebra. And the reason I'm going to trust my algebra is because as I take a second look at this, this looks not really a lot like 47.74 degrees. To me, that looks a lot more like closer to 30 degrees. So understanding that probably this triangle here is not a very good representation. It's probably actually more like this. Right? It's probably a little more like that. And you can see that in this representation, that does look more like it's something like 49.72 degrees. Okay? So that's where, I try to be accurate when I sketch my picture at first. And I don't apologize for necessarily not doing a great job on that sketch, because I think it's instructive, because you shouldn't waste a ton of time trying to make your triangle perfect. And if that's the case, then every once in a while you're going to kind of go back and say, well, that actually doesn't look completely accurate now that I take a second look at it. And that's okay. All right. And then finally, let's go ahead and find B here. B is, I'll go back to blue, I guess. B is, and I'll use the law of cosines, so we'll take the square root of 97.84 squared plus 131.08 squared minus 2 times 97.84 times 131.08 times the cosine of 49.72 degrees. So my B is approximately 100.85. And so I can go ahead and put that right here, 100.85. Okay, and you can see here also, these are supposed to be pretty much the same, but this one's clearly shorter than B. So again, my picture is imperfect. But then we want to check our green solution, right? How's our green solution doing? Well, we should find beta, right, by taking 180 degrees minus my 47.74 degrees minus my 97.46 degrees. And that gives me a beta of 34.80 degrees. Okay, and you can see again, didn't do a very great job on this picture either, because this looks like a smaller angle than 34.8 degrees, right? But I'm going to chalk that up to poor drawing instead of poor algebra. I can look through and notice that my algebra looks good on everything. And then finally, let's go ahead and do the law of cosines. So this will be 97.84 squared plus 131.08 squared minus 2 times 97.84 times 131.08. And poor planning on my part, I've run out of room, so 34.80, that should be up there. And so when we do that, we get about 75.45.